So the next topic we need to talk about would be probability. So we're working here in chapter 3. We're on some real basic probability topics. We're not going to get too deep into probability in that you could spend multiple semesters studying probability. We'll get through the basics to get us through the statistics components that we'll use probability for. So our basic objectives here in the chapter are that we want to understand the terminology that goes with probability, what a probability is, and some of the notation that we're going to use. We want to determine whether or not two events are mutually exclusive and whether two events are independent. That's going to help us to calculate probabilities using the addition rules and multiplication rules. And then we'll try and look at Venn diagrams or tree diagrams. This will also help us to calculate probabilities using these different rules. So let's start with terminology. So first off, probability. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. Okay, so it's the calculation, the certainty of a particular outcome is the way you can simplify probability. So an experiment is a planned operation carried out under controlled conditions. So sometimes we'll calculate a probability by doing an experiment, and then we'll look at the results. Okay, the results should not be predetermined. We should look at the results and then record the results in that experiment, in which case we're going to call that a chance experiment. So if we were to flip a coin twice for our chance experiment and record what the outcomes were after we flipped the coin twice, that could be our chance experiment, where each outcome is just a matter of chance in terms of flipping the coin, how many times it flipped over before you caught it. One part of working with probabilities is calculating a sample space. So first off, we need to look at the results. The results of an experiment are going to be our outcomes. And the sample space is the set of all the possible outcomes. Okay, so the set of all the possible outcomes would be our sample space. So there are three ways we really can represent a sample space. One way is to just list what all those possible outcomes are. But if there's a large number of outcomes, you can miss one very easily. So what we tend to do is try to organize our sample spaces a little bit, in which case we can create a tree diagram to help make sure we get every possible outcome listed, or we can use a Venn diagram to do that as well. We usually use the uppercase S to denote what the sample space is. So if we were drawing a sample space, say, okay, here is our sample space, we'll call that S. And then all the events that make up the sample space could be listed with, say, circles. And we typically would list an event with a capital letter, say A or B or C. And those are all the different separate outcomes that would come together to create our sample space. So if we wanted to say, let's flip a coin, okay, we flip a coin twice. What's the possibilities? Well, the sample space is heads or tails. Okay. Sorry, I flipped the coin once, not flipped the coin twice. If we flip the coin twice, we could get a heads and then a heads. We can get a heads and a tails. We can get a tails and then a heads, or we can get tails and then tails. So that would be the sample space if we flip the coin twice. If we flip the coin once, it's just heads or tails. So those are all the different options you can get when you're flipping a coin. Heads being one option, tails being the other. So an event is any combination of outcomes, right? So you look at the outcomes, you look at combinations of outcomes. Usually we use capital letters, like I said a second ago, A and B, to represent those events. And so if we said P parenthesis A, that would be the notation of saying probability that event A occurs, okay? So we're trying to calculate the probability that event A occurs. So if event A represents getting ahead, then probability of A, P parentheses A, would represent the probability that you get ahead. Okay? The probability of any outcome is the long-term relative frequency of that outcome. So it's basically saying that if we were to look at something occurring over and over and over again, let's say we flip a coin 1,000 times and record how many heads we got or how many tails we got. That was essentially the probability of getting aheads would be based off of that long-term relative frequency of that outcome occurring. Our probabilities will range between 0 and 1, where 0, okay, is going to be the probability that event will never occur. So if you got the probability of event A to be 0, that's never going to happen. If you got 1, that means the event is always going to happen. So that's your scale there, 0 to 1. So 0 on this end, 1 on this end. Never happening, always happening. And then you can get anything in between, so probability of, say, like 0.5 or a half, basically says you have a 50-50 shot that it's going to happen or not. So, you know, if you look at what's the probability of you passing this class, that's not an actual probability, but what's the probability of you passing this class, you would want it to be a lot closer to 1 than, say, 0.5 or even, hopefully not 0. Okay? Another example would be we flip a coin repeatedly, so 20,000 times, okay? The more you do it, the better. The relative frequency of heads should get closer and closer to the actual probability, which would be 0.5. You have 1/2 chance of getting heads and getting tails. So it's a 50-50 shot, right? And so when they say 50-50 shot, that means they have a probability of 0.5. And if I did it, say, 20,000 times, I should probably get pretty close to 10,000 heads if I recorded it. Maybe not exactly 10,000, but pretty close. I should get closer and closer to that 0.5. Outcomes. Sometimes we label outcomes as equally likely. Okay? This is pretty important, because an equally likely outcome means that any outcome has just as good a chance of happening as any other one. So flipping a coin is a primary example of that. You have just as good a chance of getting a heads or a tails. And oftentimes you'd say the coin is a fair coin. That means it's not weighted one side or the other. So if it's weighted on one side or the other, then you don't have an equally likely chance, right? It's always going to fall to the heavy side. But if it's a fair coin, it's not weighted to one side or the other, and you have just as good a chance of getting a heads or a tails. Roll the dice. Roll a 6-sided die, okay? You got 1 through 6. Again, if it's a fair die, you're going to see this a lot. If it's a fair die, it's not weighted towards one end or the other. So in which case, you could just get a good a chance of getting a 1, as a 5, as a 4, whatever. Okay, so it's an equally likely outcome. If I had it weighted towards one side, it would have a better chance of falling on that side. It's not always going to fall on the weighted side, but has a better chance of falling on the weighted side, in which case it's not an equally likely outcome to get a 1, 2, 3, 4, 5, or 6. Okay? If you were just doing a true-false question, you had no idea how to do the question. Okay? You were just simply guessing. You would have just as good a chance of getting it right or getting it wrong because you'd have true or false. Pick one. Just like the heads or tails. All right, so if we want to calculate a probability, we want to do the actual calculation of a very simple probability. Okay? What we can do is we can look at a very basic formula. And it says, all right, if you have equally likely outcomes, okay? This is pretty important here, is that we have these outcomes in our sample space that are equally likely. What we can do is we can look at the number of outcomes in the event that we're looking for, divided by the total number of possible outcomes that there could be, which would be the number of outcomes in our sample space. So if we were going to toss a fair dime and a fair nickel, the sample space would be heads, heads, tails, heads, heads, tails, tails, tails. This is similar to the one I just gave you a couple minutes ago, flipping a coin twice. Here they're just saying it's two different coins. So let's say first coin is dime, second coin is nickel. So heads, heads, nickel and dime are both heads. Here the dime is tails, but the nickel is heads, etc. All right, and I said, what's the probability you get one of the coins to be a heads? Well, if you're looking at this, how many different ways could you get one heads? Well, there's 2 different ways to get one heads. Okay, it's either the nickel's heads or the dime's heads, but that's the only way you can get one heads to pop out. So the number of ways that your event can occur getting one heads is 2. How many possible things could happen when you flip the 2 coins? Well, there's 4 possible things that can happen. So the way you calculate the probability that you get one heads would be 2 divided by 4, or 0.5. You could write it as a decimal. You could write it as a fraction. Usually if it's a fraction, you would want it to be a simplified fraction. But that's it. That's how you calculate a probability. Pretty simple when you look at it, but it really would require you to have equally likely outcomes in an event. Roll a die. So we roll a six-sided die. What's the probability that we're going to roll at least a 5, which means 5 or more? So it's a 5 or a 6. So you look at this. Okay, here's our sample space. These are all the outcomes that you can get when you roll the dice. And so the number of ways that you can get your outcome, which would be a 5 or a 6, is there's two ways, right? You get the 5 or you get the 6. So the probability that you get your event to occur, this event we're calling E, there's two ways it could happen, 6 total possibilities in all. So 2 6, 1/3 would be the simplified fraction. Okay? Again, it's best to simplify your fractions as much as possible when you're calculating your probabilities using fractions. All right. Another one. Okay? So use the following information to answer the next questions, in that we're looking at a jar of jelly beans. Okay? Jelly bean contains 22 red jelly beans, 38 yellow jelly beans, 20 green, 28 purple, 26 blue, and the rest are orange. Right? So you look at this and go, okay, well, what's the probability you're going to get a blue? Well, how many blues do I have? I have 26 blues. Okay? How many do I have total? 150 total. So the probability I'm going to get a blue is the number of ways mine can occur over the total number of possible events. So 150 jelly beans. How about getting a green? Well, there's 20 greens, 150 total. So 20 over 150. How about getting an orange? Well, you have to figure out how many oranges you have, since you have all these and you know there's 150 total, and you would find out you have 16 oranges out of 150 total. And purples, 28 out of 150 total. And reds, 22 out of 150 total. And yellows, 38 out of 150 total. Now, none of these fractions are simplified. So you could either turn them into decimals, which is probably the more common thing you're going to see, is all these written as decimals, or you can simplify the fractions. And I know most of the time students don't like simplifying the fractions at this point. You've done a ton of that in algebra. So just put in your calculator, get the decimal, give me 3 decimal places. Typically, you'll see 3, what we call 3 significant digits, 3 non-zero decimal places. So if we're working with probability for outcomes that are not equally likely, then what we have to do is an experiment. Okay? Rather than flip the coin and record the outcomes, right, which would be experiment, what we did previously is we just look at what are the possibilities. We never actually flipped the coin. Okay? We could figure out what the sample space is in those previous ones without doing anything beforehand other than looking at what the possible outcomes could be. But that's only when you're dealing with equally likely outcomes. If you don't have equally likely outcomes, then you actually have to perform an experiment. And you have to record what's happening in your experiment to be able to calculate a probability. In a lot of cases, we're not going to have equally likely outcomes. And sometimes we assume we have equally likely outcomes, and we actually don't. So, here's math professors in Europe had their statistics students measure the euro coin, and they discovered that, out of 250 trials, when they flipped it, the heads came out 56% of the time, and the tails 44% of the time. Well, in 250 trials, you should probably get closer to 50-50 than that. So then, as they did it more and more, they realized they actually weren't getting the 50-50 shot on the heads and the tails. And the coins weren't really fair. They were weighted actually more one way or another. So you can figure out whether or not you're dealing with an equally likely outcome sometimes by performing an experiment. Lots of times we just assume that we have equally likely outcomes. That's why your problems are going to say you're dealing with a fair die or a fair coin. So we can assume it, but in reality, a lot of situations don't have equally likely outcomes. So we work with probabilities when outcomes are not equally likely. So let's say the probability that a knee surgery is going to be successful, right? You don't have just as good a chance of it being successful and not being successful, which are really the two outcomes. Because there's also some gray area. It was like kind of successful, like you can walk, but better than before, but not great. But anyway, you don't have just as good a chance of a success or a failure when you're having knee surgery. All right. So if we look at, say, the probability of success is 0.85. Okay. What that's basically telling you is that 85% of knee surgeries are successful. All right. So if we wanted to sort of use that and maybe find the probability that 2 knee surgeries are successful, all right, well, we could say, all right, well, what are the possibilities? We could say that the first one's successful and then the second one isn't. First one's successful and the second one's also successful. First one's successful and the second one isn't, which is different than the first one not being successful and then the second one is, and then they both just fail. Okay? But we can't use this to calculate the probability that you have 2 knee surgeries that are successful, even though you go, okay, well, what's the probability that one's successful? There's 2 different situations where one's successful, and then divide that by 4. You can't do that. Why? Because the probability of one of them being successful isn't an equally likely outcome. But this 85% tells us, all right, well, you don't have just as good a chance of having a success or a failure. So we can't use this idea to do a probability that we get, say, 2 successful knee surgeries. And so this is why it's important to understand, do you have equally likely outcomes? Flipping a coin, rolling dice, picking cards out of a deck. These tend to be your equally likely outcomes. Real world scenarios like having knee surgery tend to not be equally likely outcomes. As we start looking at more and more involved probability situations, equally likely or not, we're going to talk about the addition rule and the multiplication rule, which really revolve around the A or B situation or the A and B situation. So when we think about A or B, there's really 2 different types of or statements that you can make in, say, the English language. It's the inclusive or and the exclusive or. The inclusive or, A or B or both. Okay? That's the inclusive or, and that's the or we're going to talk about. Or there's the A or B that's exclusive, where it's A or B but not both. So we're going to do with the inclusive, A or B or both. Okay? So if I said A is this list of numbers and B is this list of numbers, okay? Tell me what's in A or B or both. Well, you would say basically everything here, and there's some things that are in both. And I'm not going to write them twice when they're in both, like say 4 and 5 are in both, but this is just a list of everything that's in A, B, or both. Then we have the A and B, which is a little bit simpler. It's what is in both at the same time. Okay? An outcome is in A and B at the same time. So again, if A is 1, 2, 3, 4, 5, and B is 4, 5, 6, 7, 8, A and B would just be the ones that are in the overlap, which would be 4 and 5. So or is everything, including the overlap. A and B is only the overlap. Okay? We're going to do a lot of probabilities as they relate to decks of cards. I like doing card probabilities. It comes up in talk about gambling or whatever else. It doesn't really matter. But I like card probabilities. I think they're fairly easy to work with. So you should familiarize yourself with what's in a deck of cards. So we have clubs, we have spades, we have hearts, we have diamonds. We have ace, 2, 3, 4, 5, 6, 7, 8, 9, and then jack, queen, king for each one. There are 52 cards in total. Whenever we deal with a deck of cards, we don't talk jokers, standard deck of cards. So 52 cards in our deck of cards and 13 of each suit. So 13 clubs, 13 spades, etc. Okay? So you got to familiarize yourself with this so that we can do some probabilities. Another term you're going to have to get familiar with is a term called a complement. Complement of event A. This would be the symbol we use for complement. You put the little dash at the top. Sometimes we read it as prime, but we'll read it as complement. And it's basically saying that A does not occur. So if you found the probability that A happens, and then you find the probability that A doesn't happen, together, that should give you every single probability, which should give you a sum of 1. So the probability of A and the probability of A complement added together should always give you 1. So let S be the sample space. So let's say a random sample space is 1, 2, 3, 4, 5, 6. Doesn't matter what that stands for, 1, 2, 3, 4, 5, 6. If A are the outcomes 1, 2, 3, and 4, then A complement would be that not happening, so the only other option would be that complement is 5 and 6. So if I said, okay, what's the probability that you get A? Well, A, 1, 2, 3, 4, so there's 4 of them out of 6 possibilities. And the probability that you get A complement, well, there's 2 of them out of 6 possibilities. Add them together, you get 6 out of 6, and you get 1. Another probability notation that you're going to have to get used to is something called a conditional probability. And a conditional probability is A given B. So the probability that A occurs given that B already occurred. Okay? So it's conditional in that A has to happen after B already happened. You assume B already happened. Okay? And the notation is this straight line, P A dash B. So that straight line is a given or conditional probability. And again, it's the probability that A will occur given that B already occurred. Okay? It's not the probability that A happens after B could happen. You're assuming that B already happened first. Okay? And what happens lots of times is that will reduce your sample space, because if you take the fact that B already occurred, sometimes you have to remove that from your original sample space. So here's an example of a conditional probability. Well, not a very good example. It is an example. So suppose we toss a fair die, okay, six-sided die. The sample space should be a 1, 2, 3, 4, 5, or 6. But let's let A be that the face is either a 2 or a 3. So we get a 2 or a 3 after we roll it. And B be that the face is even, so a 2, 4, or 6. So let's say we want to calculate the probability of A given B. Probability of A given B. So what does that mean? The probability that we get a 2 or a 3 given that we only are looking at evens. So the idea here is you would say, all right, well, only one of these is an even out of the 3 possibilities. So if I look at how many of these are here, I say, well, there's only one of those, because I'm only saying given that I'm only looking for evens, out of the 3 possible evens total, so my probability will be 1/3. Again, this isn't the greatest example of a conditional probability, but it gets the job done. And after we get more into some formulas, we'll have a better way of calculating conditional probabilities. So another topic we need to talk about is independent and mutually exclusive events. This will help us more with our formulas for more complex probability situations. So here's a Venn diagram. Okay, Venn diagrams, this is a way of sort of representing sets with these circles and seeing that the circles overlap, meaning that the sets or the sample spaces of the different events overlap. Okay, and we could talk about probability of A and B or A or B and conditional probabilities by looking at these sample spaces. But this should represent all the particular events that could be in a sample space. This is a particular event, this is a particular event, and this is where those events overlap. And so we could talk about A or B, which would be all of this, including all of this and the overlap. A and B would be only where they share, which would be this intersection or this overlap here. And then we could also talk about the conditional probability in this picture. So if we want to look at a formula for calculating a conditional probability, in this case we're doing the probability of B given A. You have to understand that the probability of B given A is not necessarily the same as the probability of A given B. Okay? So the order does matter. What we can do is we look at 2 separate probabilities here. This is the probability of A and B. This symbol right here is our intersection symbol, and you can use the word and instead of that symbol. So we said that A and B would be all these elements, okay? And then A is everything that falls in here. So if I could count up how many times my event could occur in A and divide it by the total number, and I can figure out how many times my event occurs in the intersection and divide by the total number. I can find these individual probabilities and divide them, and that'll be another way of calculating this conditional probability. Okay? So we look at Venn diagrams to help us understand maybe some of these formulas and use it to try and count up the number of events we have in each one. Once we have that conditional probability formula that we just talked about, we can actually rewrite that with a little bit of algebra, move this to the other side of the equation by multiplying, and we can get a formula for the AND probability as well. Okay? So the probability of A and B can be found by doing the probability of A times the probability of B given A. Now, again, this is if a conditional situation is involved. Is B given A different than just B itself? Is B dependent on A? So then we start talking about independent events versus dependent events. Okay? Independent events are two events that are not going to affect one another. Event A and event B are completely separated, that one outcome does not affect another outcome, then they are not conditional, they are independent. However, if they are dependent, then the given probabilities will affect things a lot. So if it's independent, A given B is the same thing as A, and B given A is the same thing as just probability of B, if they're independent, because it doesn't matter what happens with B or A, the probability will remain the same, right? And therefore, if we're trying to find the AND probability formula, we would just do the probability of A and B by doing each one separately. Usually, independence versus dependence is greatly affected by whether or not we talk about sampling with or without replacement. With replacement means, let's say we took a deck of cards, and I pull a deck of cards out, and I pull one card out of the deck of cards. I look at what it is, and then I put it back into the deck of cards, and then I go and pick another card out of the deck. Well, that was done with replacement. And what happens is the second card I pick has the same chance of occurring as the first card I picked. Like the probability hasn't changed. The number of cards has not changed. The number of clubs has not changed because that first card was placed back into the deck, as opposed to without replacement. Without replacement, I would pull a card out of the deck of cards, look at what it is, and then put it to the side. Then I would take another card out of the deck of cards. If I do that, there are now less cards to pick from for my second card than my first card. And when we do that, what we assume on the second card is that the first card you picked out was the card you were looking for. So if you said, what's the probability I get a clubs on the first card? Okay, and then I put that to the side. I'm going to assume I got a club, and then I'm going to go back and say, what's the probability now I get my second card, knowing that there are now less clubs and less overall cards. So then in that case, the second one is affected by the first. So if we look at this example and determine whether we have independent or dependent events based off of this with or without replacement concept. And so think about if we have a deck of cards, 52 cards in the deck, we have all four suits. The suits are clubs, diamonds, hearts, spades. We've already gone through that. You should generally know your deck of cards. Remember, 13 cards from each suit. So you go from ace, sometimes they call that a 1, but we're going to say ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, then jack, queen, king. That's all the same suit. So let's assume we pick 3 cards at random. All right. So we pick 3 cards. First card, queen of spades. Second card, king of hearts. Third card, queen of spades. Can you decide whether or not that was done with or without replacement? And I would say it has to be with replacement, right? Because there's no way you can get the queen of spades and then the queen of spades again if you didn't put the queen of spades back in the first place. Okay, there's only one queen of spades in this whole deck. So that had to have been done with replacement in that scenario, right? How about we do it again? We pick cards and we get the queen of spades, we get the king of hearts, and we get the jack of spades. Can you decide if that was with or without replacement? Well, it actually could be either. You could have pulled each card out and put it back in the deck and gotten a different card every single time. That's possible. You could have also done it without replacement. You could have took the queen out, put it on the side, then pulled the king out, put that on the side, then pulled the jack out, put that on the side. You didn't get the same card twice, so that actually could have been with or without replacement. It's hard to tell just from the card you picked, but definitely the first one had to have been with replacement. So then you worry about, are these events independent or dependent? And whenever you do without replacement, even if you get a different card the next time around, it's still dependent on what happened before it, because there are less cards to choose from. So if the probability of the second card being pulled is affected by the first card being pulled in any way, it would be a dependent situation, and that would definitely happen without replacement. With replacement, the probability will not be affected. All right, so we're going to look at also mutually exclusive events. So independent, dependent, okay, and then mutually exclusive is another thing we need to talk about. Mutually exclusive are events that cannot occur at the same time. Okay? Cannot occur at the same time. And so if you said, what is the probability of A and B, which is both occurring, that should be 0, if they are mutually exclusive. Okay? If they're mutually exclusive, they can't happen at the same time. Therefore, the probability of both A and B occurring would be 0. Right? So here's a quick example. Suppose you have a sample space of 1 through 10. Okay? Whatever that stands for doesn't matter. That's your sample space. Let A be 1, 2, 3, 4, 5. Let B be 4, 5, 6, 7, 8. And let C be 7, 9. So clearly the probability, if we look at the probability of A and B, okay, probability of getting this and this, which would be where are we in both at the same time, well, 4 and 5 would be A and B. And so the probability of that would be those 2 out of the 10 total, so 2 out of 10. Since that's not equal to 0, then A and B are not mutually exclusive. Okay? How about A and C? Well, A and C don't share anything. Okay? So if you looked at that, since there's nothing in common there, then the probability of A and B, well, there are 0 that are both in A and C at the same time, so 0 out of 10, which would be the same thing as just 0. And therefore, A and C are mutually exclusive. Okay? They cannot happen at the same time. If you see two events that overlap, and say if you drew them as a Venn diagram, those would be not mutually exclusive, because there's some situation where they happen at the same time, as opposed to if you drew the Venn diagram with two completely separate events and they never overlap, then they would be mutually exclusive. This is going to be important when we're really doing a formula-based calculation for probability. So we have two basic probability rules we're going to work with, the AND rule and the OR rule. And these will be formula-based rules to look at probabilities. And sometimes it's simpler for you to just straight use the formula rather than overthinking the problem and trying to count up your sample space and to break it down into more simple probabilities. So that's what these rules will do. So first is the multiplication rule, and that will be for the AND probability. And when you see this symbol here, here and here, this stands for the word AND. And this is all contingent on understanding whether or not A and B are dependent or independent. And the formula changes. In a way it changes. I mean, it essentially stays the same formula, but you would have to look at it as in a different way. So let's just say A and B are dependent. If A and B are dependent, then what you would say is the probability of A and B would equal the probability of A times the probability of B given A. Because B is dependent on A, this probability is extremely important. In order to calculate B, okay, in order to calculate the probability of B, you have to think about what happens with A as well. And that's only because they're dependent on one another. If they're independent, then we know that this given probability is really just the probability of B itself. Probability of B given A should just be the probability of B. It's not dependent on A, so the A doesn't have any bearing on this, and therefore just gives you probability of B anyway. And then the formula would just be the probability of A times the probability of B. But it is really the same formula in essence because this equals this in the independent situation. So that just turns into that probability. So we're going to have to look at some examples to clear this up a little bit more, but this is the more formula-based approach rather than just looking at the sample space and counting up how many elements we have in each situation. Then there's the addition rule. So we have A and B are, events on the sample space. We have to worry about what the addition rule, which is really for our OR probability. So this symbol right here, here and here, this is our OR probability symbol. And this really is contingent on whether or not our events are mutually exclusive or not. Okay? If the events are not mutually exclusive, which means that they could happen at the same time, there's an overlap between A and B. And if we look at this OR probability, which is the addition rule, because when you find the probability of A or B, we're going to use addition in our formula. We look at the probability of A plus the probability of B. The problem, though, happens when they're not mutually exclusive is you're counting certain things in both of these groups at the same time. So you're making a double count. And since you're double counting the ones in both situations, you have to subtract those out. So we have to subtract out the probability that we're both in A and B at the same time. Okay? That's the overlap. We have to subtract the overlap. If they are mutually exclusive, then that overlap ends up being 0. And if we subtract out 0, it really doesn't do anything. So we really could just do the probability of A plus the probability of B in the OR situation. And again, that's only if they're mutually exclusive. And we wouldn't be double counting any values in the sample space because they don't overlap at all. So here's an example. I have a bunch of them we're going to go through, but here's one of them. Juan is trying to choose where to go on vacation. His two choices are New Zealand or Alaska. Okay? He can only afford to go on one vacation, though. The probability that he chooses A, which is New Zealand, is going to be 0.6. The probability that he chooses B, which is Alaska, is 0.35. So if I try to figure out what's the probability that he goes both to New Zealand and Alaska, well, that should be 0 because he said he can't afford both. He can only afford one. So the probability of A and B is 0. Okay? So that being said, you're never going to happen at the same time. So these are definitely mutually exclusive situations, right? So then if I wanted to find what's the probability that he goes to either New Zealand or Alaska, okay? What's the probability that he basically goes to one place, one of the two places? Well, I look at the probability of Alaska plus the probability of New Zealand. Oh, I reverse that. Probability of New Zealand plus the probability of Alaska, which is 0.6 and 0.35. And I'm going to subtract out that mutually exclusive, the fact that it's 0. I don't have to worry about that. And I'm going to get 0.95. So the probability that he picks one of those two places based off the probabilities given is 0.95. And using our addition rule for the OR probability. So what if I said, what's the probability it doesn't go anywhere? Well, the probability that he picks one of them is 0.95, so the probability that it doesn't go anywhere would be the complement of that, and so that would be 1 minus 0.95, so 0.05. Okay. Here's another one. Student goes to the library. B, the student checks out a book. D, the student checks out a DVD. So the probability that the student checks out a book is 0.4. Probability the student checks out a DVD, 0.3. The probability that the student checks out a DVD, given that they also got a book already, is 0.5. So this is a conditional one. Again, they got the DVD, given that they already got a book. That's 0.5. Where did they come up with these numbers? They're just made up. Okay. So I want to find the probability of B and D and the probability of B or D. Again, I just want you to get used to the formula-based approach to this. So the probability of B and D, this is your and symbol. So this would be the formula we use, the probability of B times the probability of D given B occurred. And since we have the probability of B to be 0.4 and D given B to be 0.5, the and says multiply, and if we multiply, we would get 0.4 times 0.5, we would get 0.2. So that's the probability of B and D. What's the probability a student checks out a book and checks out a DVD? Okay. How about the probability of B or D? So the probability a student checks out a book or a DVD. Remember, this or is the inclusive or, so it could be or both. Okay. So if we look at this and go, okay, well, we have to calculate this probability for or. The formula, we should start off by going probability of B plus the probability of D minus the probability of both. We're going to assume that they're not mutually exclusive. And if they happen to be, then we'll just be subtracting out 0. But we assume they're not mutually exclusive to start. I think that gives us less chance of making a mistake here. So the probability of B is 0.4. The probability of D is 0.3. We already found out the probability of both is 0.2. So put that in here. Add, subtract, you get 0.5. So the probability that a student checks out a book or a DVD or both is 0.5. Okay, so let's do a few more and or probabilities so you can get more comfortable with this formula. So here's a couple of or probabilities. A card is drawn from a standard deck, 52 cards. Find the probability that that card is a queen or a club. And so when we're looking at these, it's really about mutually exclusive. Can it both be a queen and a club at the same time? In this case, yeah, it can. So if we're going to use the or formula, it should be that the probability of queen or club should be the probability of a queen plus the probability of a club minus the probability of a queen and a club. Okay, so both. So let's look at each one individually. Queen. How many queens are in the deck? 4. How many cards in the deck? 52. Okay. How about the probability of a club? Well, there are 13 clubs. How many cards? 52. So the probability of a club is 13 out of 52. Minus, how many cards are a queen and a club? Well, that's 1, the queen of clubs. So 1 out of 52. And the whole purpose of this formula and the reason why we subtract the 1 over 52 is because if you think about it, the queen of clubs is counted here and the queen of clubs is counted here in the cards that we're counting up to come up with this probability. So we're double counting the queen of clubs. We're counting it in the queens and we're counting it in the clubs. So we have to subtract one of those out because we don't want to double count anything when we're counting up how many ways can our event occur. And so pretty simple from here, common denominator across, 4 plus 13 minus 1, and we're going to get 16 out of 15. So 16 over 15. We should simplify that, but 16 over 15 is the probability. I would turn that into a decimal. It's probably the best thing to do, and then you don't have to worry about simplifying the fraction. All right, let's look at another one. You roll a fair die. What's the probability of getting a total of or an even? Okay. This is not a good question. Let's just say not a total of 3. I've changed this question so many times. It used to be 2 die, and then you're asking the total of the die. Let's just say, what's the probability of getting a 3 or an even? Okay. So, probability of 3 or even. Okay. So another or probability. So the formula says we should do the probability of a 3 plus the probability of an even minus the probability of 3 and even. Well, here's the thing. Can a die be both 3 and even at the same time? And the answer is no, right? So they're not, in this case, these two situations are mutually exclusive. So this will end up being 0. It can never happen. You can't have a 3 and an even when you roll the die. So then in this case, we don't need that piece, right? So probability of a 3, well, 1 3 out of 6 possibilities. Probability of an even, well, there's the 2, the 4, and the 6. Okay, so there's 3 evens out of the 6 possibilities. And we're not double counting anything. We count the 3 here, and the number 3 on the die is not counted in the second group because we're only counting up the evens. So we're not double counting, which is why we don't need to subtract this out. So our final answer is 4 out of 6. Or if you want to simplify that, 2/3. Or if you want to turn it into a decimal, 0.66666, repeating. Okay. Let's look at the next one. Fair die probably is getting a, let's drop, again, scrap the total, probably getting a 4 or an even. Now, is it possible for a die to be both 4 and even? Yeah, because 4 is an even number. So this one is not mutually exclusive. So we're going to have to subtract out -4 or even. Okay? Remember, instead of the or symbol, I could also use this symbol here. Okay? That also means 4. So sometimes you'll see that. So the probability of a 4 minus the probability of even minus the plus probability of even minus the probability of both. Okay? Well, there's 1 4 out of the 6. Again, there's 3 evens out of the 6, but that 4 is counted here and it's counted in the evens. So how many 4 and even? Well, just one of them, the 4, and we subtract that out. And so the probability of getting 4 or an even would be 1 over 6, 3 over 6 minus 1 over 6, so 3 over 6, or 1/2. So hopefully that gives you a little bit more clue of how the OR probability works strictly with the formula and why the formula is what it is. I think using the formula is easier. It simplifies this rather than trying to look at this all at once and count up how many out of the total would I have in this situation. By splitting it up into individual events, I think it simplifies it. Here's a couple of AND probabilities. So, card from deck of cards is pulled out of the deck, then put back into the deck, then another card is drawn from the deck of cards. Okay, so we're drawing 2 cards out of the deck of cards, but we're doing it with replacement. It's replaced. Okay, so that means that the second card will not be affected at all by the first card. There will still be the same amount of cards in the deck, same amount of everything in the deck. So this should be a fairly easy probability in that they are independent events. So what's the probability of getting a face card on the first and a club on the second? So probability of a face card means Jack, Queen, King. Ace is not a face card. Oh, everyone asks that all the time. Jack, Queen, King, and a club. Okay? So the formula says we should do the probability of a face card times the probability of a club if these are independent. If they're not, the second probability should be the probability we get a club given we got a face card on the first one. Okay? We have to do that conditional probability. But since these are independent, we don't have to worry about that because we're doing it with replacement. If we weren't doing it with replacement, if we picked one card out of the deck, then put it off to the side, and then pick the second card, and we're wondering what the probability that that's going to be a club would be, that would be a little bit trickier. Reason being is because now there's less cards in the deck of cards to pick from, and the second event would be affected by the first. All right, but we don't have that scenario. We just have face card, club, independent situations. How many face cards are there? Remember, Jack, Queen, King, and there's 4 of each. So that means 12 face cards altogether out of 52 cards. Times how many clubs? Well, there's 13 clubs out of the 52 cards. So the probability, you would have to multiply this, and you should know how to multiply fractions, straight across, okay? And you can get your answer. So if we do this, we would get 156 out of 2,704. I would probably just turn that into a decimal, so 156 divided by 2704. So roughly, let's erase this here. We would get as a decimal 0.0577. We usually like to use 3 significant digits, so 3 non-zero digits here. It's just a general rounding rule for probabilities. The problems typically will tell you round to 3 decimal places, 2 decimal places, but there you go. Or we could have just left it as a fraction, but this isn't simplified, so that would be problematic. All right, let's look at the next one. If you toss a fair coin 8 times, what's the probability of getting all heads? All right, well, think about it. If you flip a coin, then flip a coin again, then flip a coin again. Every time you flip it, is what happened before that going to affect the next one? No, right? They're all independent flips. I can get heads on the first and heads on the second, and they have nothing to do with one another. All right? So in this case, it's independent again. So really what we're looking at is the probability that we get a heads and another heads and another heads and another heads and another heads, and we're going to do this 8 times. Since they're independent, it's just the probability of a heads times the probability of heads times the probability of a heads, etc. Again, 8 times. Okay? We can do each one by themselves. And so the probability of getting a heads is 1/2. So this should be 1/2 times 1/2 times 1/2 times 1/2 times 1/2, 8 times. So how many do I got here? 1, 2, 3, 4, 5, 6, 7, 8. And so it should be 1/2 to the 8th. Right? So if you do 2 to the 8th, that's 256. So 1/256. Again, because they're independent, I don't have to worry about, oh, I got a heads on the second, given I got the heads on the first. Every flip of the coin is independent. So hopefully that clears up a little bit about the and probability. Again, I think the formula helps simplify how you would calculate the probability. Oftentimes people overthink these probabilities and how to count up how many ways your event could occur because they look at the whole picture, okay, rather than looking at the individual situation. And if you can break it down to an and probability or an or probability, you can figure out what formula you need. Oftentimes these probability questions require you to have some prior knowledge of how certain things are working, like cards, knowing what's in a deck of cards, dice, etc. If I gave you gambling questions about, say, roulette, you'd have to know how the game of roulette works at the casino. Another way around that to ask questions of probabilities where you don't really need any prior knowledge would be with a contingency table. So it's also good for just organizing data and working with data in general. When you're not doing, like, say, gambling probability questions, this is primarily how you would see probability questions set up. And so, a table just organizes everything so that you can count up how many values are in your sample space and how many ways that your event could occur much easier. So here's an example. It's a study of speeding violations and drivers who use cell phones. And so they broke their data down into different groups. So everyone who uses a cell phone while driving is in this row right here, okay? And there's 305 people. But then they broke that out as 25 got a speeding violation and 280 didn't. And then these are all the people who didn't use cell phones while they're driving. 450 people total there. And then they broke them out again here and here. You see, used a cell phone, didn't use a cell phone, that should be all the people that we're talking about. That adds up to 755, so that's our total number of people in our study. Or you could look at it as speeding violation. These are the people who got speeding violations, okay? 7 people total. These are the people who didn't get speeding violations, 685 people total. Again, that should give you your 755. So we know how many people are in this study total, 755. So if we ask a couple questions as it relates to this, as in terms of probability, all the numbers are there. We just have to know what numbers to use. And so that's the nice thing about contingency tables. Again, you don't need any prior knowledge. All the data is in front of you. You just need to know how to pull it out to find your probability. Okay, so with this table, we'll ask a couple of questions. First, find the probability that the driver is a cell phone user. Very simple. So we look at how many cell phone users are there, okay, and how many people are there total. So using a cell phone while driving, that's this column right here, and there are 305, okay, people using a cell phone out of the 755, so 305 over 755. Again, I would simplify that or turn it into a decimal, but pretty easy. Those are the numbers you would use. Next, driver had no violation in the last year. So what's the probability the driver had no violation? Okay, so these are all the people who had no violation. There were 685 of them total. So the probability should be the number of people who had no violation, which would be 685 out of the 755 total. Pretty easy again. Next question. Probability the driver had no violation in the last year and was a cell phone user. Now, as far as these probabilities go with the ands and the ors, etc., with the contingency table, it's actually easier just to count up the values you want than to try and use any type of formula. So if you think about it, what people were in the no violation and the cell phone users at the same time. So here's the cell phone users and here's the people who had no violation. So that's my total number right there. So if I'm looking at the probability, there were 280 people who were both cell phone users and had no violation last year out of the 755 people total. I don't need to use a formula and calculate the multiplication rule, etc. It's pretty easy to count up the number I need when I have the table in front of me. Here's another one. Driver is a cell phone user or the driver had no violation in the last year. So we count up how many people had is a cell phone user. So if we look at it, these people are cell phone users here. Okay, let's use a different color. These people are cell phone users. Okay, and these people had no violation in the last year. So we want to do this group. Okay, let's use an eraser. It's getting too messy. So we want to use this group or this group. Well, notice when we're counting it, these 280 people would be the ones we would count twice. So we're not going to do that, right? We know we don't want to double count. So I'll say 25, the 280, and the 405. That's how many people total are going to be the ones we want out of the 755 people. Okay? So what's that going to be? It's going to be 685 plus another 25. So that would be what, 710? So 710 people out of 755 people total would fit that criteria of being a cell phone user or had no violation. So we could use the addition rule. We could do the basic sum rule where we subtract out. But if you look at it, we know about the double counting thing now. We could just count up all the people that fulfill this requirement. All right, let's do another one. Let's look at a given one. Find the probability driver is a cell phone user given the driver had no violation that last year. So basically this is saying we're not looking at the total of 755 people. The given tells us that the group we're actually looking at is we're really looking at the people who had a violation in the last year. These are the people who had a violation in last year. This is the total group we're working with. And out of that group, how many used a cell phone? Okay, that's how you would read this. They used a cell phone given we're working within this group of people who had a violation in the last year. So the probability in this case would not be out of the 755, but really would only be out of the 70. It's a smaller group we're working with because of the conditional, the given probability. And 25 people out of those 70 fulfill this requirement. They were drivers that used cell phones, and they fell into, given that they fell into they had a violation. Let's look at another one. So here, this one has to do with athletes, and they stretch before they exercise and whether or not they had injuries. So this table gives us a bunch of totals, okay? But again, sometimes they don't give you totals. They'll just give you these four numbers, and you have to total them up. So anyway, these are all the people who stretched. 350 people stretched. These are all the people who don't stretch, 450 people total. And then there's people who had injuries and people who didn't have injuries. Total, there's 800 people in this, because if you add these and you add these, you get 800. So in this case, find the probability the athlete stretches before exercising. So these are all the people who stretch. There are 350 of them out of the 800 total. So 350 out of 800, that's your probability. That's not simplified. Again, I would turn that to a decimal or simplify the fraction, but nonetheless, there's your answer. All right, let's look at the next one. How about the probability that an athlete stretches given they had no injuries, right? So now, given they had no injuries, the no injuries is the group we're working with, okay? These are all the people who had no injuries, okay? 514 people total. Out of them, how many of them stretch before exercising? 295. So we have 295 people out of the 514 that had no injuries. That would be the probability in this case. So then the given probability, the bottom number always has to be adjusted to not being the total of everybody, but just the total of the ones you're working with in the given scenario.